Hello. Okay, so in this video we're going to be going over line integrals through vector fields. Line integrals are one of my favorite concepts in vector calculus. They have so many real-world applications. You'll see line integrals all the time in physics. Examples are like line integrals are often used for calculating work, and they can be used to calculate center of mass. It's found in Ampere's law and Faraday's law. So many applications. You'll definitely be seeing line integrals. Anyway, so first, let's get started. We need to understand what vector fields are. So a vector field is a function that associates each point in space with its own vector. Vector fields, again, are all around us. There are a few real-world examples. Sort of relates back to like calculating work and Ampere's law and Faraday's law. Gravitational fields are vector fields. You can see each point in space, like every point that my finger is at, it is being affected by some force of gravity in a direction, and that's a vector. Anyway, gravitational fields, magnetic fields, electric fields, and also fluid velocities and fluid flows, like here. That's my rough interpretation of some fluid flow. But anyway, yeah, so you'll also see like vector fields all throughout fluid mechanics and fluid dynamics. So now to calculate the line integral of a curve through a vector field. So what actually is this saying? Here we have our vector field f, and we're plugging in r of t. What this gives us is the vector at point t, we'll say like here, on our line r. So in this case, if we move our point up a little bit, we'll have this vector, which is happening at point t on this line, be inputted here. And then we're going to dot that with the derivative of our line at point t. Now, our derivative of our line is going to be the tangent vector to r at point t. So here, if we have, let's say, now let's look over here. We have this vector at point t, right there. Ooh, mixing up my markers a bit. And then we're going to have the tangent vector of our purple line, which will be something like that. And then we're going to take the dot of this vector and this vector. All right, let's put this to use with some actual numbers. So here's our vector field, which is actually shown here. Its x component is 0 and its y component is 2y. And then down here we have our parameterized line, our parameterized curve. So our first step in the process is to find r prime. All right, our r prime of t is 2 comma negative 2t. Let's plug it into our integral. So it should come out to be something sort of like this, where we have our vector field with r of t plugged in. This is the y component plugged into the y for our vector field. And then we have r prime of t. I did also decide to just arbitrarily integrate from 0 to 10, which on our vector field, or our line, would look something like this. So from here down to somewhere like that. All right, so this next step that I just did was just doing the dot product of these two vectors. Our first component is going to equal 0 because it's 0 times 2. So it ends up that our dot product is just 2t squared plus 8 times negative 2t. So let's write that out. All right, so we got, oh, that's perfect. We'll end up with t to the 4th minus 8t squared from 0 to 10. So I'm going to move over here. We'll just plug that in. We got 10 to the 4th minus 8 times 10 squared, and then that minus 0 to the 4th minus 8 times 0 squared. That's 0. So we just have this, which is 10,000 minus 800, and then that's going to end up being 9,200. There we go. There's our line integral.